Hello, everybody. I'm a psychiatrist and clinical pharmacologist with over 20 years of industry experience in large and small pharma and 10 years in academic clinical research, with a strong interest in and experience with intelligent automation. I'm a member of the ARIS Global Advisory Board, and as such, I present on ARIS Global's behalf on the expansion and automation of pharmacovigilance services. Over the next 20 minutes, I intend to give you a comprehensive overview on automation of pharmacovigilance activities. But first, we need to set the stage by reviewing the full scope of pharmacovigilance activities suitable for automation. And then we will discuss how to identify which processes and activities should be prioritized for automation. We will review strategies on how to implement machine learning in production, and then more specifically, how intelligent automation is realized for the identified use cases using attribute identification from case narratives as an example. When we talk about machine learning, we also need to talk about training data for machine learning algorithms. And finally, I summarize the automation development from current state to the foreseeable future. So first, let's align on what we consider within scope of pharmacovigilance activities. In its simplest form, we're talking about data acquisition, data analysis, and the communication of results. From an automation perspective, these buckets are of increasing complexity from left to the right. But let's look behind the veil. This is a high-level process schematic, and it is probably familiar to many of you. On the left-hand side, we have the AE receipt from various sources, booking, triage, and data entry into the database. In the middle column, here depicted in green color, the database content is worked on through ICSR adjudication, signal detection, signal and safety issues assessment, taking into consideration external data from varied sources such as literature, electronic medical records, claims data, and freedom of information data. On the right-hand side, you can see what is labeled as communication, the 7 and 15-day expedited reporting, the periodic aggregate reporting, and the various ad hoc communications, either company internal or to external to health authorities. So we can differentiate two major approaches from an automation perspective. The primarily transactional activities depicted in blue, and including ICSR processing activities from case intake to distribution, and the primarily cognitive activities ranging from ICSR adjudication, signal detection, issue assessment, and ad hoc communications. So now that we have explored the scope of the automation task within pharmacovigilance, we can see what this means for the development of the respective tools. Here is a high-level description of the pharmacovigilance automation trajectory. The arrow represents a crude timeline. Now, in the beginning, there was no big bang, but rather a gradual development of activities, largely managed manually. With the advent of databases and workflow systems, mostly labor-intensive transactional case processing activities received electronic support. And over the last 5 to 10 years, more and more transactional activities were automated via rule-based programming or robotic process automation, as long as clear decision trees are available for that respective process. Now, robotic process automation is now increasingly enhanced through natural language processing and sometimes also natural language generation. However, activities to date are still primarily focused on transaction-rich case processing. Well, some may interject that there was indeed some automation of the more cognitive-oriented signal detection activities. However, this is referring primarily to electronic scheduling systems for disproportionality algorithms, an entirely transactional activity, and does not address the actual signal adjudication, which is a primarily cognitive function. Now, with the more recent development of AI-associated cognitive computing technologies, such as machine learning, deep learning, and reasoning, application support of primarily cognitive functions becomes available. If we jump back to the previous slide for a second, it is apparent that this opens much of the data analysis and results reporting process activities to electronic support, and automation. Much of this is likely to manifest within the foreseeable future, but not without some caveats. This is well summarized by Bill Gates. He remarked a couple of years ago that never before in history has innovation offered the promise of so much to so many in so short a time. Turns out that this statement expresses an eternal truth with which we are living. Year over year, technology evolves faster and faster, ensuring that Bill Gates' quote remains valid. However, as we can envision the promise of emerging technology, we also need to acknowledge that the realization of these ideas is very complex. The further a vision reaches, the greater the degree of complexity. Now, as we develop the vision, promises and hopes are generated, often far-reaching. However, the development of the tools to fulfill these promises is expensive. Clearly, there is so much to do. But another eternal truth you are all familiar with is that resources are always limited. So now what? How are we to operationalize the accelerating technology promise for Ares Global customers? Well, the answer we found is, in one word, prioritization. A pragmatic, comprehensive, systematic, balanced, and rational prioritization approach is needed to optimize the implementation of the available technology for the benefit of the system users. To prioritize, we need to understand the full breadth of activities within the domain, as we just reviewed on the previous slides. So to that end, a full process analysis of the domain-specific activities is the basis to subsequently dissect the process into distinct use cases, which can then be compiled into a comprehensive list of all the use cases. Each use case is then evaluated based on a matrix of criteria to reflect, first, the business value of the automation of the specific use case, and second, the associated technical effort. The scoring for each criterion is then used to associate the respective use case with a priority category. A welcome byproduct of this comprehensive analysis is the identification of synergies within the domain, allowing resource optimization. On this slide, you can see a reflection of the prioritization matrix as it is currently in use by Ares Global. I find the complexity a bit reminiscent of an airplane cockpit, and analogous to the lighting of the buttons intended to direct the pilot's attention. The spreadsheet uses color coding of text and highlighting of fields. There are a confusing number of buttons on the dashboard, but in the end, the airplane brings its passengers and cargoes safe into its destination. Note that this is not a Boeing 737 MAX cockpit, however. So this pragmatic, comprehensive, systematic, balanced, and rational prioritization approach ensures that the resources are appropriately directed to the automation opportunities providing maximal benefit to system users. It will ensure a continuous, value-based stream of innovations over years to come. Besides the identification of the use cases for automation, an additional consideration is how machine learning capability is applied. Specifically, how will the machine learning algorithms be updated? How will they learn? I have here summarized three strategic approaches. The static approach freezes the machine learning model after the training run to then use traditional validation methods similar to the methods used for rule-based programming. A new training run to update the algorithm then requires a full validation. This is contrasted by the dynamic approach. It keeps the model in continuous training mode. Any new data entered into the system will also serve to update the algorithm. This approach is analogous to how humans learn and incorporate new experiences on the spot into their responses. Unfortunately, there are not yet any established guidelines available, let alone regulatory guidelines on how to validate a system that by design evolves its specs over time. So a new validation approach has to be developed for this type of system. A hybrid approach freezes the model for periods of time while simultaneously evaluating all incoming data for the potential effect on the model. If the accumulating data indicate an improvement over the existing model, a mini training cycle is initiated. While the validation for the hybrid approach is more in line with current methodologies, it is advisable to develop a largely automated validation to realize the efficiency potential of the hybrid learning model. So now that we are clear about the machine learning strategy, I will use the example of attribute identification from case narratives to explain the synergy between the more traditional rule-based programming and machine learning models. The attribute identification utilizes natural language processing with a hybrid NLP service. The left-hand side schematic depicts the traditional rule-based system, while the right-hand side reflects the machine learning component. Both components work synergistically, each with distinct areas of responsibility to optimize the attribute identification. I will describe the application of the machine learning model in more detail on the next slide. We need three key ingredients: a machine learning model, a training dataset, and a validation dataset. The training data is used to train the machine learning model. Text attributes are identified and contextualized through a model-specific relational attributes of text strings. Upon completion of the training, the model performance is tested with the validation dataset. The validation dataset is a separate dataset, not part of the training data. If test performance is satisfactory, the model is then added to the repository. Model specificity and performance are subsequently used to select the models that will be used in production. When a case narrative is then fed into the production tool, it is dissected into relational attributes, assessed for relevance to the desired attributes, and the attributes best compatible with the production specification are provided as output with a confidence score to indicate the degree of certainty for the extraction. A threshold can be set for this confidence score to determine when human verification of the extraction is needed. So to summarize, we went from the application requirements derived from the business use cases to the model performance requirements, the criteria needed to be achieved by the application to meet the standards set by the business case. We will now move on to the data quality requirements to ensure effective model training and validation. And I want to spend a little more time on discussing training data on the next slides. Similar to how humans learn, machine learning algorithms learn better with good and particularly precise training material. The more unambiguous the training data elements are, the fewer training data are needed for the machine learning algorithms to pick up the respective underlying patterns. Well, that means that fewer machine learning model iterations are needed in model development. Typical methods to generate good training data are to scrub training data from ambiguous and incomplete data, as well as to annotate training data. Data annotation is the process of adding metadata to a dataset. This metadata usually takes the form of tags, which can be added to any type of data, including text, images, and video. So what does this mean for pharmacovigilance? Particularly in situations where training data sets are relatively limited in quantity and where the data sets are rich in non-essential distracting data elements, adding comprehensive and consistent annotation is a key part of developing a training data set for machine learning. This allows supervised machine learning models to recognize recurring patterns in annotated data. After an algorithm has processed enough annotated data, it can start to recognize the same patterns when presented with new data that is not annotated. Now here, I have a few examples for limited non-essential information-rich data sets. That includes signal detection and evaluation, pharmacovigilance agreements, aggregate reports, and literature reports. This slide shows an example of a semantic annotation similar to how it can be used with pharmacovigilance data. The desired data elements are color-coded according to their respective categories. The machine learning algorithm uses the categorical attribution in combination together with the relation of the data element within the text position and can analyze for the signifying patterns that will eventually allow them to recognize such data from annotated data. So we talked about limited data sets. ICSR data are certainly not limited. In fact, ICSRs are the most ubiquitous pharmacovigilance data. They are really in abundance and usually have much less unrelated data elements per record. In addition, the original case reports have been annotated through the extraction of the needed data elements which are captured in the associated database record. I refer to the relation of source document and database extraction as a surrogate annotation in this context because it is missing one element of traditional annotation. And that is the extracted data elements are no longer within the context of the original text location. Hence, the machine learning algorithm will look at every occurrence of the data element within the source text and analyze all for identifying patterns. Now, is this surrogate annotation sufficient to allow using ICSR data directly from the database for machine learning algorithm training purposes? This is a relevant question as it would save significant resources not having to go back annotating data, but rather feeding the data directly into the machine learning algorithms from the database. I studied this question and published the study in Clinical Pharmacology and Therapeutics last year. The results confirm the viability of using ICSR data directly from the pharmacovigilance database for the training machine learning algorithms. A larger training data set is needed, but ICSR data are typically available in large quantities. So let me shift gears a little and contrast the current state of pharmacovigilance process to what we can expect in the foreseeable future. Depending on the database system and version currently in use, many companies still have a highly manual ICSR process and workflow as depicted on this slide, let alone any of the cognitive areas of pharmacovigilance such as case adjudication, signal detection, and aggregate report authoring. Now, companies who employ a more modern database, specifically the Ares Global LifeSphere Multivigilance version 10, have already introduced a significant degree of automation of the data intake and data entry process, as well as the ICSR distribution. These are the workflow steps more heavily governed through distinct processing rules. In the foreseeable future, the ICSR workflow will be automated end-to-end. The human role in ICSR processing will evolve to an oversight role. It will include the adjudication of machine-identified data attributes associated with confidence scores that fall below a defined threshold. The number of cases processed per person will increase significantly over time as the machine learning algorithms become increasingly adjusted and trained. Regarding the user interface and user experience, the emphasis will shift to the facilitation of the interaction between human intelligence and artificial intelligence, the HI-AI interface. So now I hope I was able to give you an overview of the approaches and strategies for implementing intelligent automation in pharmacovigilance. And I thank you for your attention.